Good morning, everybody. Well, we're getting to the point where it's afternoon now. It's lunchtime. It's Tuesday, March 24th. Mr. Frechette, back at you in the math world. A little math 8 action with volume of cones and spheres. But before we get started with that, I hope everybody is healthy and happy, working on some academics, having some fun too on the side. I hope you guys are getting outside as well, when you have a chance. But today we're going to make it a little interesting. I wanted to actually calculate the volume of actual cones, but to be honest with everybody, being stuck in a house with my family and different things, Mr. Frechette ate all the cones. Yep, I did. I ate all the ice cream cones, and I didn't have any, so blame it on me. So I had to find a picture of an actual cone, so we can all dream that there's that cone with ice cream and it's in our hands, but that's not the case right now. So we're looking at volume of cones and spheres. I got an actual ice cream cone, or something that looks like an ice cream cone. And then we have an actual bowling ball, which it'll be great to, I haven't gone bowling in a long time, but it would be great just to get out and go bowling. But obviously that's something we can't do right now, but, hopefully soon enough. So I'm staying positive with that. So moving on. Ice cream cone, little story about ice cream cones. Love ice cream. Ice cream is like my all-time favorite dessert. And I'm a soft serve guy. I like custard. But the one thing I've never understood about an ice cream cone is how come they can never, ever, ever get the ice cream all the way down to the apex of the cone or the actual tip of the cone. That kind of upsets me, when I go through and I only, once I eat the ice cream that's on top of the cone and I get down maybe, a few inches, I'm just eating cone. And don't get me wrong, I like an ice cream cone. It's great to eat it. But, I'd like to have ice cream throughout. And even when I was a kid, I also found if I bit the apex at the bottom and tried to suck the ice cream out, that it was very difficult to do because the ice cream never went all the way down to the apex of the cone or the tip of the cone, which, man, that can be tough, man, especially for me being a kid. I want the ice cream. I want the ice cream throughout. I don't want to get cheated. I want all the ice cream I can get. All right, well, story time's over with Mr. Frechette and his crazy obsession with ice cream and ice cream cones. So, volume of cones and spheres. You see a whole bunch of work on here, okay? So we're going to go through it. Okay, so first things first. If we look, and I want to use my pointer so you guys can have it. Let me get my pointer over here. So you see over here, we have a diameter. Our diameter, this looks like a circle, so our diameters are linked from one end of the circle to the other. And then we have an actual height, and that's from the center of the actual opening of the cone all the way down to the tip or the apex that we talked about. Okay, that's very different than this slant height here. Slant height is not the same as actual height. So keep that in mind. The numbers are not the same. So when you're measuring volume of a cone, you need to make sure you're measuring or you have the height from the center of the cone itself or the circle at the top all the way down to the apex or the tip, not the slant height, which is right here. So without further ado, we have a height of 6 inches. We have a diameter of 2 inches, so we have a little more work to do, but it's not a big deal. Over here, our volume or our formula for volume of a cone is 1/3 pi times r squared times h. And this is all multiplication because we have our numbers directly next to either a variable or another number itself. So when we work this out, we want to go through different things. And I'm just putting an equal sign in here because this is what the volume is. When we get down there, I'll put what volume equals. So we have, as you see, I'm writing my second step. So we have 1/3 times pi times 1 squared. Well, where did Mr. Frechette get the 1 from? Well, we have a diameter here. And we need the radius. So R stands for radius. And radius is half of the diameter. So half of 2 is 1. So that's how I got the 1. And that's 1 squared times 6. And, just to show you that, let me put my, right, that's just times 6. Right, no difference. So going through, I want to make sure we're back to the laser pointer of some sort. So over here, going down, I wrote again. So now you have 1/3 times pi times 1 times 6. Remember, I'm using PEMDAS as I go through this. Up here, I simplified my exponents first. I didn't have any parentheses, but I have to do my exponents before I can do multiplication. That is a rule. You need to know order of operations, otherwise you're going to make careless errors. So you have 1/3 times pi times 1 times 6. Now we're dealing with all multiplication. So going from my second step to my third step, I did 1/3 times pi, and then I just simplified 1 times 6, which is 6. Okay, multiplication and division, they're interchangeable. It doesn't matter what you do first or second. When we go through that, still got multiplication here. So before I got to 2 pi, I did, what is 1/3 times 6? Well, 1/3 times 6 is just 2 pi. So 2 pi, right, is right there. In some cases, when you get to upper level math, you'll leave it in terms of pi. That means you will not take 2 and multiply it by pi and get a decimal, which we did in our final answer. But in this case, we are, because we're dealing with an actual volume and we want numbers to represent that. So I'm going to put this in my calculator again. So if we take 1 divided by 3, and then we multiply that by 6, you'll see that we get 2. So that's how we got 2 pi. So I'm just using my calculator to show you guys that. So in the end, when we take 2 and we multiply it times pi, 2 times pi right here, you see what well, there we go again, my mode. My mode in math print, I got to make sure I'm in classic. So we're going to clear that out, and when I go 2 times pi, you see I get the 6.283185307. I rounded it to the nearest hundredth place, and we simply got our volume. And now I'll bring the V in. Our volume is 6.28 inches cubed. So that's what this cone is in terms of volume. Now that's basic calculation, right, of the volume and how much this cone can hold. Now from Mr. Frichette's story that's usually not the case. You go to the ice cream place, that doesn't mean you're going to get 6.28 cubic inches of ice cream. They kind of shortchange you. From what I had said, you're most likely getting less of that. But that's just Mr. Frichette complaining, so I'm not going to complain. I'm going to be positive. Okay, so moving forward. If we look at a sphere, in this case, we're looking at a bowling ball, right? So a bowling ball, right, we have one dimension that we're really dealing with, and we're dealing with a diameter, although we're in 3 dimensions, so you're looking at cube. So because you got a 3-dimensional object with the cone and with the sphere. So with this, we have our formula. Volume equals 4/3 times pi times r, which is radius, cubed. Right? So we're not squaring it like we did in when we calculated our volume of a cone. When we do a volume of a sphere, we are actually cubing it. So keep that in mind. 4/3 times pi times r, which is radius, cubed. Okay, so this calculation a little bit on the simpler side. So you're just plugging or substituting in all your values for what we have. So once again, we have volume equals 4/3, and I left the pi out when I was writing this. Remember, don't make those careless errors. Write all your steps. So we bring pi in, and then you're saying to yourself, how did Mr. Frichette get 4.25? Remember, like we talked about over here with our cone. This is a diameter. This is also a diameter. So we have to take for us to figure out our radius, a radius is half your diameter. So you got to take 8.5, and I put in 85, 8.5, and divide it by 2. And you get 4.25. Okay, 4.25 is our radius, and that's cubed. So down here, you see what I've done. Now, once again, PEMDAS, or order of operations, or please excuse my dear Aunt Sally, are very important. All right, I don't have any parentheses, but I have exponents I have to deal with. So I have to take 4.25 and cube it first. I cannot multiply and divide first. I have to deal with the exponent. So that's what I'm going to do. And when I deal with the exponent, I get a number that's 76.7, and it goes on for a while. So I'm going to show you guys that. 4.25, we hit our little caret key and we raise it to the 3rd power. You get 76.765625, and that's what it goes to. Okay, to finish up, we had the 76.765625 number, and we would have to multiply that by 4/3. Okay, because, so if I multiply this by 4 divided by 3, I get 102.3541, which is basically what we get either way. You got like 102.6, which is fine. Different things happen when you round it. So we have 102.6, and then what we're going to do is we have to multiply this by pi itself, and you notice in the end, we get 321. So as you notice, when you round, different things happen. So I've used actual numbers. That's why up here, that's why I got volume equals 322.641 inches cubed. So that's the volume in and of itself. You see the numbers are a little bit different depending on whether you round or not. So you got to be careful and you got to read directions. That doesn't mean we're wrong, but then again, you got to be careful when you're going through. As you can see, when I'm using actual numbers and I'm multiplying different things, my numbers were a little bit off because of rounding. So they're not at exact when I did this beforehand. I was just showing you, going through using the calculator in of itself. So this is volume of cones and spheres. Hopefully this helps you get through Mrs. McKeechick and Mrs. Dombrowski's assignments this week. If you have any other questions, I will be on Google Classroom and I will be doing different things. So keep that in mind. I'm here for you. So if you have any other questions, you can message on Google Classroom. You can email me. We can go from there, and hope to see everybody very soon.